All right, what's up, guys? So today we're going to be talking about AP Physics. Specifically, we're going to be talking about work with constant force. So before we really get into solving a problem that has to do with solving for work, we have to first understand what work is. So what work is formulaically is work is equal to the force times the displacement. Force times displacement. And an important rule that has to be followed when it comes to solving for work is that force and displacement must be parallel to each other. So they must be parallel to each other. So this is a very, very important rule. So let's say you have a force going in the right direction, but you have a displacement going vertically upwards. You really can't, at face value, solve for work because those two directions are not parallel to each other. They're perpendicular to each other. So you can't use those two values and solve for work. But let's say you had a applied force going upwards and you had a displacement going upwards. Then, of course, those are both parallel to each other, so you could solve for work. So this is a key, very, very important rule when it comes to solving for work. So when we are solving this problem, we're going to double check to make sure that both our force and our displacement are parallel to each other so that we know that, whatever situation we have, it will be valid to solve for work. So without further ado, let's get started with the problem. So we have a problem here, and it tells us that there is let me erase this really quickly. It tells us that there is a crate, and it weighs 1,200 newtons, and it rests on the floor. It asks us how much work is required to move it at a constant speed. This is very important when it says constant speed, because it gives us a little idea of the forces that are acting on this crate, and we know that if it's at a constant speed, all the forces that are acting on this crate must be at equilibrium. So they're asking us to solve for how much work is required to move the crate at a constant speed. If move it 5 meters horizontally with a frictional force of 230 newtons, and B, 5 meters vertically. So, let's get started with part A. So the best way to start part A is really to draw a free body diagram. You know that in part A, they tell you that there's a frictional force of 230 newtons. So if they tell you explicitly that there is a force acting on this crate, the best thing to do is draw a free body diagram to make sure that, we can understand exactly what equations we should derive with this frictional force into consideration, so that we could get an accurate way of solving for force and in turn solving for work. So if I was to draw a quick diagram, if the red represents ground level and the orange or yellow represents the crate. We know that this crate is 1,200 newtons. We know that really its weight or its gravitational force is 1,200 newtons. They give us that right in the problem. So they tell us automatically, explicitly, that there is a frictional force of 230 newtons. So I'm just going to label this force going towards the left as our frictional force, and we know that the frictional force is 230 newtons. We know that because it's on a surface, there has to be a normal force going upwards, perpendicular to the surface. Ground level is the surface. And we know that there's a gravitational force because it has a gravitational force. It is matter. It has to have a gravitational force, on it. So there is a gravitational force that exists on this crate. And the final force that we ought to draw is an applied force. So why are we drawing an applied force? Well, if we want to displace this crate 5 meters horizontally, then we need to have some sort of applied force. For example, maybe somebody pushing constantly on the box, on the crate, with a certain applied force. So we need an applied force if we want to have this box move or displace itself 5 meters horizontally. So that's why we have to have the applied force. Now, because the problem says that we want to move this crate at a constant speed, a very important thing that we learned in dynamics was if you want to move anything in a constant speed, all the forces that are acting on that specific object have to be at equilibrium. So what that means is that the summation of all the forces that are acting on this crate have to sum up to equal 0. So that basically means, if we do top minus bottom, left minus right, that Fn should be equal to Fg, and that Fa should be equal to our frictional force, our Ff. So because we know that Fn is equal to Fg, we know that our Fn is 1200 newtons, because our Fg is 1200 newtons. So this is not really too important for us in the long run, because it's not like we're trying to move this crate vertically anywhere. So really, we don't have to pay attention to the normal force or the gravitational force. Really, they're insignificant when it comes to solving the problem. What is significant is, because we want to move it 5 meters horizontally, we should pay attention to the horizontal forces, the forces that are acting horizontally to this crate, which is the applied force and the frictional force. So what do we see here? Well, we see here that our frictional force is 230 newtons. And we know that we derived the equation Fa is equal to Ff. Our applied force is equal to our frictional force. This is because it's going to move at a constant speed, so all the forces that are either horizontal or vertical, they have to be equal to each other. So top must equal bottom, and left must equal right. So because we know our frictional force is 230 newtons, we should automatically know that our Fa, our applied force, is also 230 newtons. So this is very important, because really we want to move this 5 meters horizontally. We want to move this 5 meters. We want to move this 5 meters horizontally. And because we have an applied force in this direction, we want to move this crate 5 meters in this direction. So finding our applied force is very, very, very important when it comes to solving for our work. And just to remind you, work is equal to your force times your displacement. All right, so we kind of already did solve for our work. We've solved for our force at least. Because we know our applied force is 230 newtons, we know that that is the force that it takes to displace this crate 5 meters to the right. So we can write 230 newtons as our force, because that is the horizontal force that we use to move it 5 meters horizontally. Now we have to multiply this by our displacement. What is our displacement? Well, if this is our point A and this is our point B, we know that from point A to point B, our displacement was from 0 to 5 meters. So we know our total displacement is 5 meters to the right. So 5 meters would be our displacement to the right. So if we just type this into our calculator, if we type 230 newtons times 5 meters, 5 meters, you should get 1,150 joules for your work. Work is in joules. So let's solve part B. And I think our free body diagram wouldn't really change that much. Don't know why I erased it, but I can quickly redraw it. So if we had the ground, the crate, 1,200 newtons. We know that because for part B they don't tell us that there's a frictional force, we can assume that there are really no horizontal forces acting on this crate. So we'll only worry about the vertical forces, because that's what we're asked to solve for, the vertical displacement, 5 meters vertically. So let's see, we have a normal force going upwards because of the surface, and we have a gravitational force going downwards because crate has mass, and it subdues itself to the gravitational acceleration of 9.80 meters per second squared. So we have both an Fn and an Fg, and we want to raise this crate 5 meters vertically. So let's say we want to raise this crate from this point, from ground level, 5 meters vertically. So we want to raise it 5 meters vertically. So this would be our displacement. We go from a 0 position to a 5 meter position. So in fact, we've already solved for our displacement. Now it's solving for our force. So what force must be, put on this object, if you will, in order for it to move 5 meters. And also, you could consider Fn to actually be your Fa, because how else would you be able to move this cart up? The only way you would be able to move the cart upwards 5 meters vertically is if you had an applied force. So you could consider your Fn, your normal force, as your applied force, because that's what it is in this context of the problem. So really, Fn would be equal to your Fa, and in turn, because Fn is equal to Fa, your Fa would be equal to your Fg. So if I was to derive an equation, I would be able to say that Fa is equal to Fg. And why am I saying this? Well, because it has to be in a constant speed. And if a object is in constant speed, it has to be having forces that are in equilibrium, meaning that top minus bottom, or top must equal bottom, and right must equal left. So our applied force must be equal to our gravitational force. Our gravitational force, they already told us, is 1,200 newtons, because gravitational force is nothing but weight. So we know that our Fa, our applied force going upwards, is 1,200 newtons. So we solved for the force needed to move it 5 meters, and we have already solved for our displacement. So in turn, we've already solved for our work. So work is equal to the force times the displacement. We've solved for the work that is required, or we've solved for the force that is required to move it 5 meters up, which we've solved is 1,200 newtons. And we know that the displacement is going to be 5 meters vertically. In this case, 5 meters upwards, because it's a vector quantity. 5 meters upwards, we can say. 5 meters. And if we type this into our calculator, we should get the answer of 6,000 joules. Thank you for watching the video. Please, if you have any questions, leave them in the comment section down below. I hope that you would tune in for another video. Thank you.